In this video, we'll provide a very brief review of systems. This video is intended for undergraduate students who are about to take a course in signal processing. And the assumption is that the students have already taken a class in linear systems and signals, and this is just a review of some of the key concepts that come up in signal processing classes. So let's begin by asking ourselves, how should you think of systems in signal processing? And abstractly, a system is a black box in signal processing that takes as input signals, one or more signals, then it manipulates the signals, makes some changes to them, and outputs the resulting signals. So here is a simple diagram that is often used to describe systems. You have inputs coming in. The system is described by this letter T or any other letter that you could use, and then you have outputs from that system. Now mathematically, what is a system? Mathematically, a system is an operator. So if you are not familiar with the term operator, think of it as a function where the inputs of this thing are now, instead of single variables, the inputs are functions themselves or signals, and the outputs are functions or signals. So the system is an operator that takes as input this function, whatever this would be, and outputs another function. That's the mathematical characterization of a system, and broadly speaking, systems can take single or multiple inputs, and they can produce single or multiple outputs, and based upon that, they are given different names. For example, they are given names like SISO, single input, single output, single input, multiple output, multiple input, single output, and multiple input, multiple output. SISO, SIMO, MISO, and MIMO or MIMO. Now, systems can also take either continuous time or discrete time inputs, and they can produce either continuous time or discrete time outputs. So here are some examples. A cell phone takes a continuous time input, voice, produces a continuous time output, radio waves. Adobe Photoshop takes a discrete time input, an image, produces a discrete time output, an image. A digital voice recorder takes as input a continuous time signal, voice, and then produces perhaps an MP3 file which is discrete. So it takes continuous time input, generates discrete time output. An MP3 player is the opposite of that, takes a discrete time input, MP3 file, and produces sound that you can hear. So that's a continuous time output. Now, at the undergraduate level, the systems that are commonly studied in signal processing classes are SISO, single input, single output. That's what we will focus on from this point forward. So, how do you characterize a single input, single output system? Whether it is for designing signal processing or it is for understanding purposes. For example, you're trying to understand the system that my brain represents. Well, a complete characterization of an arbitrary system, it requires you knowing the output, which is also known as the response of the system to all possible inputs. Let me repeat that again. Complete characterization of a system requires understanding the output of the system to all possible inputs. So it's not enough. Here is an example of a system. Let's say I input to this system this function. Here is a system, and I get back some output. Now that's just one input output pair. What I want or what I need for characterization is I should know the output to every possible input. For example, if the input is this, what will be my output? If the input is going to be some other function, what will be my output? So as you can see, this is a hard task. You have to know the output to every single input. This is very difficult for arbitrary systems, except in certain cases. In particular, it becomes an easier task when you talk about systems which are known as linear time-invariant systems. These are the systems that simultaneously possess the properties of linearity and time invariance. Now, because of the ease of these systems and the way that you characterize them, most undergraduate classes actually focus on LTI or linear time invariant systems, and then in advanced classes you can sometimes think of linear time varying systems. We'll focus here on only linear time invariant systems, and we'll look at why is it easy for LTI systems to know the output to every possible input. Well, let's look at that. So first, let's understand what is a linear system. So linear systems, whether they are taking continuous time inputs or discrete time inputs, are the ones that obey the principle of superposition. What is the principle of superposition? That the output of the superposition of two or more inputs to the system is simply the superposition of the respective outputs. If one of my inputs produces a certain output, and here is another input that produces another output, and if I add the two inputs, my outputs should be added also. So I argue that human brains are nonlinear, they are not linear. For example, consider the fact that if I get $1, it makes me certain amount, gives perhaps certain amount of happiness. If I get $1 billion, that's sort of addition of $1 billion $1, the amount of happiness that I get, is it simply 1 billion times more? It's hard to say. $1 billion is a big number. I would presume that our emotions are somewhat nonlinear. Now, a system, it's again a common mistake that I've seen students make. A system is linear if it obeys the principle of superposition for all possible inputs. Just because the system obeys the superposition principle for a few inputs doesn't make it linear. It has to do that for all possible inputs. Now, we are not going to prove it, but it is actually a simple fact that if the system obeys the principle for two inputs, then it automatically is linear. And so mathematically, because of this reason, the mathematical definition of linear systems is that if I give you any two inputs, again the emphasis here is any two. If you pick two specific ones that it happens, doesn't mean that it's going to happen for some other two inputs. So given any two inputs, x1 and x2t, x1t, x2t, and given any two scalars, a and b, real or complex valued, and here I'm going to focus on continuous time systems. It's the same argument for discrete time systems. Let's assume that when I input x1t, the system generates output y1t. And let's assume that when I input x2t, the system generates output y2t. The system is linear. Now, if instead of inputting x1t and x2t separately, I add the two, I multiply them with two scalar numbers, and then I add the two, and I input that scalar combination, scalar linear combination, the output is simply the linear combination of the respective outputs. That's the principle of superposition. That's the linear system. So a simple argument is that if my input is, let's say, this is my input, and I put it in the system, and I get an output of this, and my second input is, let's say, this, and I get the output of, let's make it this. And now instead of doing this, I actually input to the system an addition of these two, which is just going to shift this input. So now instead of that, I input this thing to the system, which is the addition of this. I'm not doing any scalar multiplication. Well, what should the output be? The output should be simply addition of these two outputs, and which will be just a shifted version of my output, right? Because this is a constant. So this is the principle of superposition, or the principle of linear systems. Now, linearity is a good first order approximation of the real world in many, many instances. We like linear systems. They are easier to analyze, but they also are a good first order approximation of the real world up to a certain point. For example, if one person is saying something and the mic is recording something, you get one output. The other person is saying something, you get another output. If the two persons start speaking simultaneously, you'll get the output which will be a superposition of both the whatever they were both saying. This would of course hold up to a certain level. If they produce too much noise, then your mic may go into saturation, and that's where the linearity assumption can break down. But it's a good first order approximation. Okay, let's now talk about time invariant systems. So time invariant systems again they could be continuous time, discrete time, whatever the input they take and output they generate. The main idea is they are the systems whose operating behavior does not change with time. And so the way it is said is that the output of the system depends solely on the input and not on the time at which the input was applied to the system. Here are some examples. Human voice system is time invariant up to a certain approximation. For example, if I try to say the word ah, I say it in the morning, I say it in the evening. Up to a certain time, when I was a child, of course, the system was different, but up to a certain time, it's time invariant. I push up some air into the system, and the system produces an output, and the output stays the same whether I said it in the morning or in the evening. So it's a time invariant system. Most software like Adobe Photoshop, if you have the same version, you don't update it, it's a time invariant system. Let's say you take a picture today, and let's say you crop that picture in Adobe Photoshop today, or you do that 10 days later, the output is going to be the same. The system's behavior is not changing. On the other hand, for example, the path, or what's called the channel between a cell tower and your cell phone in an urban environment, that's a time varying system. And that is the reason that, for example, you get dropped calls. You are talking on the phone and all of a sudden your call drops. Because that's the time varying nature of the system. It wasn't static. So the system behavior has to be static. That's a time invariant system. Now mathematically, the way you pose that is that if you are given any input x1n, and again the emphasis here is that the input can be any input. If it is true for a few inputs, that doesn't make it a time invariant system. Here I'm going to focus on the case of discrete time systems to compensate for the last example where we focused only on continuous time systems. The same argument holds, of course, for continuous time systems. So the idea is that if the output of the input x1n, if the output is y1n, then the system is time invariant if I apply the input at some other time. So this is x1n minus n naught, which is that I actually moved it in time. Instead of applying it right now, I changed it by n naught amount of time. Well, guess what happened? The output is still the same. Of course, since I applied it n naught time steps later or earlier, the output has to be shifted, but it is exactly the same output, only shifted in time. So the idea again is that if I, let's say, apply this input to a system, this is 0, 1, and I get the output, let's say 0, 1, I get the output, this output. And this of course has to be true for all possible inputs, but I am only giving an example. So instead of now applying this input, I apply it, let's say 10 units away. So now instead of, I apply it at 10 and 11. So I apply the same input but after some delay. Well, what will happen? I will generate the same output, only shifted in time. The same output will be produced 10, 11, only shifted in time. Okay. Your behavior of the system does not change with time. That's all a time invariant system does. So what is then a linear time invariant, or LTI system as we will frequently call it? These are systems that are simultaneously linear and time invariant, which means they have to simultaneously satisfy both the mathematical conditions that we talked about. They satisfy the principle of superposition, and if you apply the input at a later point, they generate the same output only at a later point in time. Their behavior does not change with time. Now, what is special about LTI systems? So why are we talking about LTI systems? Remember, we said that to characterize a system, you need to know the output of the system to every possible input. That's what means to characterize a system. Well, for LTI systems, it turns out that output to every input can be known, can be specified, as long as we know the output to one input, one special input. If we know the output to one special input, we know the output to every possible input. Again, this is not true for arbitrary systems. This is a special property of LTI systems. So what are those special inputs? Well, for continuous time, the special input looks like this. This is, we write it xt equal to delta t, which is defined as following. Delta t equals 0 for all t not equal to 0. And the integral of delta t is 1. Now here is a basic mistake that students make, which is that they say delta t equal to 0 for t not equal to 0 and delta t equals 1 for t equals to 1. No, delta t at t equals to 1, we don't specify it. It is an approximation, and the approximation is carried out by saying that it takes such a high value at t equal to 0 that the integral is 1. It doesn't, that's why it has this arrow in there. Typical names for this input are it's called an impulse, or it's called a direct delta. So this is an idealization of a short duration unit area signal that peaks very high. It's really an idealization of a signal that it keeps on getting shrunk around 0, and then at 0 it peaks really high. So high that its total area stays 1. The output to this special input is called impulse response. And typically we write it as h of t. Okay. Now for discrete time, the special input looks like this. It's called xn equal to delta n, and it's completely defined. Delta n is defined to be 0 for n not equal to 0. And in the discrete case, it is true that it is defined to be 1 for n equals 1. This is a typo. For n equal to 0, this is a typo. Delta n equal to 1 for n equals to 0. Now, typical names for this discrete special input: impulse, just like the continuous case, or Kronecker delta. Now, unlike the continuous time case, this delta function, this impulse, is very well defined in discrete time. You can produce it because there is nothing undefined in here. It's 0 everywhere except at n equal to 0, it is 1. The output of this special input impulse is also called impulse response. And so just think of this impulse response. The reason it is called this way is because it is the response of the system to an impulse. So the name makes perfect sense. It is an impulse response. Now you can input, let me repeat that point, you can input an impulse to any system in the world, and the output of that impulse will be the response to an impulse. But it is only for the case of LTI systems that knowing this output, this impulse response, enables you to know the output to every possible input. So let's talk about then LTI systems, impulses, and convolution. Now, in order to know the output of an LTI system to any input, all we need is knowledge of the impulse response, which is the output of the LTI system to an impulse. Very special case. You know the output to one special signal, which is the impulse, i.e. you know the impulse response, you know the output to every possible input. So here is the case. You are given a system T, you know that it's an LTI system. This is the case of, for example, a continuous time system. It's the same for discrete time. You input this impulse, you get back an impulse response. We'll call that impulse response, so the input signal is delta t. The output signal, we'll call it ht. It's just a convention. You can give it any name, but we typically like to call it ht. And the question is, what is the output to any other input xt that is not an impulse? We know this. What is now the output to any other input? Well, the answer lies in this special formula, which we are not going to prove, that the output of any other input xt that is not an impulse anymore, the output of that input is simply given by the convolution of the input with the impulse response. And you may remember that that convolution is commutative, so it doesn't matter which way you solve it. It's similar for the case of a discrete time system. You have the output of any input xn is simply given by the convolution of that input with the impulse response. Only happens in the case of LTI systems because of the property of linearity and time invariance. This is not true for arbitrary systems. I repeat, this is not true for arbitrary systems. You may know the output to an impulse for an arbitrary system, but that doesn't mean that every possible output can be written in terms of convolution of the input with the impulse response. So here are detailed convolution formulas. Continuous time convolution, it's given by yt equals to integral of x of t minus tau h of tau d tau. You can reverse the roles of x and h because of the commutative property. Discrete time convolution, exactly the same formula. Instead of integration, of course, you have summation x of n minus m hm. You can again change the roles of x and h without any effect on the output. Now, so what's the magic of impulse response in LTI systems is there are two ways. One is that if you are doing analysis of systems, let's say you want to figure out what does the system do in a real world. There is some natural system that you want to learn about. You want to figure out how does that system behave to different inputs. Well, if the system is LTI, then all you need is to input to that system an impulse, record the output, i.e. you record the impulse response, and then you know everything that there is to know about the system. So the example of that is, let's say you are tasked with building a concert hall. You want to make sure that no matter what sound is being played in the concert hall, there isn't too much echo. Well, it's a known fact that the characteristics of echo can be modeled as an LTI system. So how do you really learn? How does the concert hall behave in response to every possible song, every possible sound that you haven't even heard about? Well, all you have to do is generate a sound that sounds like an impulse. Of course, it will be an approximation, but you generate that sound and then you record the output, whatever echo comes out of that. Using that knowledge, you are able to now reproduce the echo of every possible input because it is an LTI system. The impulse response also then helps you design systems. If you know that the system you are designing is an LTI system and you want to give certain properties to that LTI system, then all you need to ensure is that instead of focusing on too many things, designing a system, testing the response of the system to every possible input, all you do is you design the system such that it has a certain impulse response. You test the response of the system to an impulse, you analyze that, which of course is part of what signal processing helps you do, and if it has the right characteristics, you know that your LTI system will do the right thing on all possible inputs. So an example of that is if you want to design an equalizer that increases bass of a song, well, that equalizer can be modeled as an LTI system, and all you have to do is then focus on designing the right impulse response. And because of this property that LTI systems are completely characterized by impulse responses, often what you see is that instead of this figure in books of systems, if the system is an LTI system, what you see is an equivalent picture where the system is itself replaced by just the impulse response. So you list down if it's continuous time ht, or if it's discrete time you list down hn, and this is an equivalent definition because an LTI system is completely specified by an impulse response. Now, of course, if in your linear systems and signals class, you must have learned that impulse responses of LTI systems tell you a lot more because they completely specify the system. In particular, two things that you should remember are that the impulse response helps you figure out whether your system is stable or not. What is a stable system? A stable system is something, if I, for example, generate a little bit of input, the output should be a little bit, it shouldn't become unbounded. If my input is bounded, if I'm speaking on this microphone and my voice isn't really shattering everything, then the output that this microphone should generate shouldn't shatter anything either. So that's the definition of a stable system. The output remains bounded for bounded inputs, and for LTI systems it turns out that the impulse response can help you figure out whether the system is stable or not. So in the case of a discrete time LTI system, if your impulse response is absolutely summable, which means if I take my impulse response, I sum up absolute value, and if this comes out to be less than infinity, then my LTI system is stable. Similarly, in the case of a continuous time LTI system, I take my impulse response, I do absolute integration. If the integration is less than infinity, then it's stable. Now, in the case of continuous time LTI system, this is actually also a necessary condition. It has to satisfy this for the system to be stable. Causal systems, that's another thing that impulse responses can help you figure out. So what is a causal system? A causal system is one that is not clairvoyant. A causal system is one in which the output of the system depends only on past and current inputs. Since a system cannot figure out what's going to happen in the future, its output at this point doesn't depend upon future inputs, which is only possible for clairvoyant systems. So no practical system would be non-causal. Now, LTI systems, they are causal if and only if the impulse response is 0 for all times t or n less than or equal to 0. So in general, whether a system is causal or not, figuring that out is really hard. But if it's an LTI system, then all you have to look at is whether the impulse response starts before t or n equal to 0 or not. And here is a reason for that. So let's say that I input n equal to 0, I input an impulse, and my output comes out to be, let's say, n equal to -1. So what is this thing saying? This is saying that I had an activity in my system at time 0, but somehow my system already knew that I would apply an input at time n equal to 0, and it generated an output at time n equal to -1. So it effectively anticipated clairvoyantly that there will be an input at time n equal to 0 and generated an output before time n equal to 0. So this, of course, means it's a non-causal system. So what you need is causality, means that h of n has to stay 0 for all n less than 0. Otherwise it's non-causal. And similarly, h of t has to be 0 for all t less than 0. So again, the impulse response, a very small thing, but if it relates to the LTI system, it tells you so much more. It helps you figure out what is the output to every possible imaginable input. You don't have to input that thing to figure out how the system would behave. It tells you about the stability of the system. It tells you about the causality of the system. So hopefully these things will stick around throughout your signal processing career.